Hello, do you hear me? Okay. Thus today is the 8th of May, and I am happy that I can see and hear, even virtually, my new student. So please give me a short introduction. So your name is, how should I call you?
Abu Zaid, you can call me Abu Zaid.
Write on chat the answer.
Yes, okay, of course.
In chat. Abu Zaid. So I will tell you Abu Zaid, yes?
Yes, yes, okay.
Okay. You asked me yesterday a question, yes? What?
Actually, I saw the question on the book and the material you sent me,
Yes, it is not
and
your question. It is a good question, and it is based on the equation of state. Do you know the equation of state?
I'm not sure.
PV is equal to MRT. Yes, and if you divide, let's say if I can use, again, I cannot use it, okay. My whiteboard. You are not alone?
Oh no, actually, I'm not alone.
No, okay. Have you seen the essay you have to solve?
Yes, I saw it today, and I think I'll
Yes.
send it after tomorrow, maybe.
Okay, so
But have I more time because I prefer to take my time to study better. Then I can start with it. You want to join me? No.
I don't know what. I cannot share. You are sharing this. I cannot share the screen.
I am sharing the screen.
No, you are not sharing, but I cannot share the screen.
Okay.
I will start again.
Uh-huh.
Do you see anything?
Yes, yes, I can see your
Okay,
screen.
okay. This is the essay you have to solve, yes? But you are free to use all sources, yes? Open sources or books or lectures, whatever. But you have to solve all these items. First question is to make for me a list with units for pressure, for temperature, energy, power, mass, volume, yes, whatever. But in international system, and where it is the case for temperature and pressure, energy, uh, uh, power, yes, you must indicate also other units accepted in thermodynamics, and further, you must write down the connection between the unit in the international system and the specific unit. Did you understood what you have to do?
I have an idea, but I will start read. I will finish the material first.
Yes, I also uh, uploaded you some courses, some lectures, yes?
Yes.
So one of it has the name Units in Thermodynamics.
Yeah, I saw it.
Yes, so this is what I mean, yes? But you can collect also from your books at home or whatever it would be interesting for you,
Hmm.
yes?
Okay.
I have to create a file. Okay. Second question. So, second question, to explain what do you understand by overpressure, meaning a pressure higher than the ambient pressure, named barometric pressure, and what do you understand by vacuum, meaning a depression, meaning a pressure under the barometric pressure. Is it clear for you?
Not very much.
So if I tell you the overpressure in this vessel is 1 atmosphere, what is the real pressure in the vessel? It
I don't
will
know.
be a sum between the overpressure and the ambient atmospheric pressure, meaning it will be 2 atmospheres. So overpressure, as the word says, it is a value over the ambient pressure. Now it is clear?
Yes, yes.
Yes.
But your screen is not moving.
My screen is not moving.
Yes, it's still in the opening the AC number one, AC number two.
Okay, yes, I didn't open. Do you want
Uh-huh.
this one?
No, I thought you opened it, so
No, no, no.
okay.
But I can so I mean this, yes? So you can put units as much as you want.
Hmm.
But import, you can put also flow rate or whatever, and use better the symbols from at home. So as you are using them in your home country.
Uh-huh.
Yes,
Okay.
not to have any other question.
There.
So you see do you see my
The screen.
the screen? Yes.
I see the screen, but I think it's not moving.
No, now I moved it. Yes. This
Still
is
not.
what you say. Also, you know. Yes.
So you open the file.
Yes, I opened the file.
It's
Don't you
still
see?
no, it's still nothing.
Because mm, you see it.
Yes, now I see it.
Okay. So I made this file. Uh, so you can see here it is an example of units, yes?
Mhm.
Yes, so you must look in the internet or whatever about these. Yes, so these are the units in thermodynamics. So the notion of overpressure is known for you now.
Yes.
You can look also in the internet. You write here of over pressure. I don't know if you will find something. Over pressure, Wikipedia.
Mhm.
Uh, Above normal, okay, effect, calculation. Uh, okay, the calculation is, here it is not okay, what I see. So it is above the normal atmospheric pressure. The normal atmospheric pressure, if you click here, you see it is what? It is 101,000 or 1.01 multiplied by 10 5 Pascal.
Mhm.
So here you see it, yes? You see it?
Yes.
Okay. So this is the values that you must know by heart.
Okay.
Let's see, science direct. Oh, oh no. Okay. So point number 3. What is a perfect gas, an ideal gas, and a real gas? So the ideal gas is a gas that doesn't exist. It is a model. It exists only in our mind. We say all the molecules are spheres. They move respecting the mechanical laws. They have no mass. They have no density. They don't interact in between each others, and so on. Thus, it is uh, very important to stress out that this ideal gas was developed only for enabling some mathematical equation and demonstration and so on, because the ideal gas doesn't exist. There is a special gas named perfect gas that has some resemblance with the ideal, with this model. And this is the gas that exists, but it has a low density. Low
Mhm.
density means low pressure and high temperature. You know that zero is the lowest, 0 Kelvin is the lowest temperature you can reach.
Yes.
So our temperature now, let's say 20 degrees, yes? Or I don't know, 17 degrees. 17 degrees plus 273 is 300 Kelvin. 300 Kelvin is already a very large amount. So it is a high temperature. So the answer to this question is the following. A perfect gas is a gas that exists having a low density, meaning low pressure, high temperature, and under these conditions, it uh, resembles to some properties from the list for the ideal gas. Is it clear?
Yes, yes.
Okay. So what is a real gas? A real gas is, as the word says, real, and it has some specific properties that the perfect gas doesn't show. The most important is a change of phase. Uh, so you can imagine the um, vapors, the water vapors, they can change by reducing the temperature uh, and condensating. They can change in what? In water, in liquid. Yes, and this phenomena is accomplished due to the internal energy of the system, and it needs, or it needs, sometimes it needs energy, otherwise it is exhausting energy. So the process is occurring of fast changing is occurring at constant temperature by a given pressure, but during the process, uh, uh, heat as energy form is exchanged. Means you can gain or you can lose energy. For example, when you want to turn water into vapors, do you need energy or you lost energy, or the system needs energy or loses energy?
Need energy, of course.
Needs energy, yes. And the energy is depending on what, on your opinion?
Energy.
It
On
depends first of the quality of the, now we are speaking of water, so water vapors. It depends on the pressure and on the temperature. Yes, all these data, pressure and temperature and so on, are put together in charts. I don't have a chart in English. Thus, I can um, upload you some charts and tables in Romanian. I can show you some, and if you agree, I can load the files, but to translate them now, especially for you, it will be not very easy for me. Normally, you need such tables. I will give you an example. Okay, I will go into my my campus because I cannot access them from here. Do you see my screen?
Yes.
Yes. Okay, so here it's written tables and diagrams. Yes, I will upload you them as well, but first I want to show them to you if they are useful for you. So first of all, it is a table with units. I think you will understand this table. Even here it is written in Romania because you see the units.
Mm-hmm.
So lungime, length, volume, weight, flow, temperature. Yes. So this is a table.
Okay.
You can. This is a continuation. Here it is interesting for the pressure. See how many units we can use. Yes. For energy, for power, for density, energy density. So here you have a lot of units. Then you have the symbols. The symbols meaning exa, petra, tera, giga, mega, what it means. Yes.
Yeah.
Here you have for uh, all four processes, polytropic, adiabatic, isothermic, isobar, isochoric, you have the formulas.
Mm. Oh
All
yeah,
the
I think it will
formulas.
be useful
Yes. So I will load this.
because while I'm reading, to make a summary, I'm writing this kind of
Yes. Yes.
equation, but with this
So
table, it will be easier.
it will be easier for you. So
Yes.
uh, so here you have here all kind of formulas, and what do you don't understand, you write these words in Google Translator,
Of course.
find out approximately what it is. But
Uh-huh.
normally you can see here, and some words are resembling to English, and okay, Romanian is not such a difficult language, on my opinion. I don't know what is your opinion, but do you speak French? No,
Actually, no, only
no,
English.
only English, but your English is good. In the university, you are getting the class in English or
Yes, yes, in English.
in English? Okay, that's why your English is so good.
Actually, it's not that because I have lots of colleagues that bad in English. But
Oh,
for me, I used a lots of movies, and
okay,
that helped
so
me a lot.
then it was also a question because I made for you a list open source,
Yes.
and look how many I have for you. I will send these to you. Yes.
Okay.
And so I will upload them. Yes. And you, here I wrote here, very good, foarte bun, very good. Yes. So let's have, not all are good, sometimes you use your time. Do you see my screen?
Yes, yes, I still see it.
Yes. Okay. Happy you don't hear it. You must always skip. So, Professor
Uh-huh.
Professor Dave, he's very good.
Mm-hmm.
You hear something?
Not, no, yes, I hear a little, but not can't
Okay.
understand.
So you will receive this list from me, and whenever you have time, it is not mandatory, but it will help you a lot. Yes,
Uh-huh.
for me it is a very difficult task that in 3 weeks we have to cover 4 months, but at least I want to give you an introduction in order when you go back to have at least an idea. Uh,
Yes, yes.
do you are in the second year of study? In which semester? In the fourth semester?
Yes, the fourth. And
Fourth.
I took a summer semester last summer.
Okay. So and the marks in your country are what? From 1 to 5, 1 to 10, or what?
It's 1 to 100.
1 to 100. And which is the best?
The best is 100.
The best is 100. And up to now, in the first, second semester, what were your grades? 100?
We have grades that calculate all the subjects I took
Yes,
and take the minimum. Mine is 85.
85. So this means it is a very good or quite good or excellent.
It's excellent,
It
and there
is
is
excellent.
excellent plus.
Okay.
Yes.
So from the beginning, you must know you will receive from my side all my efforts to make you understand something, but it is quite a difficult stuff. So
Mhm.
you saw that I try to offer you twice a week uh, uh, such discussion in Zoom. Yes, I
Yes, I
already
saw.
uploaded the invitation, and uh, you have to study as much as possible. So my opinion is that if you solve this essay, uh, even based on open sources, you will learn a lot. You how to do it? You can use Word, or you can uh, write on your computer and send me a document. When you send the document, it must be PDF, and it, or you can leave it also Word, in my opinion, but it must have your name in the title and write essay number 1 or whatever it is, because
Uh-huh.
I have to collect all, even if they remain in the campus. Yes.
Okay.
So uh, the I don't know how much time I left you. Uh,
It says, I think, 3 days.
3 days. Let's see. Okay, if you have problems, essay number 1, uh, on Monday evening. But if you solve it earlier, because I will prepare a new one. Yes.
Mhm.
Also, it is important to have a look to these solved problems. Do you see the solved problems?
Yes, I can see.
Yes, they are fully solved. So you read the problem and uh, what is to calculate, and here is the solution. You have only to look after the solution and to learn from these solved problems.
Okay.
Yes, I will make more for you, but as we started so late, I couldn't do more. Yes. Okay, what is a gas mixture? What is, oh no, here we have, so number four. What forms of energy do you know? What are the, these one used in thermodynamics? Yes, what is heat, mechanical work, internal energy, enthalpy, entropy, and so on? Yes, all these are energy, heat, mechanical work, and internal energy are measured in joule. Enthalpy and entropy are, uh, let's say, more complex uh, forms, but they also deal with energy. Yes, uh, and this is seen also from the units. So, do you know the rule for heat exchange? When you receive heat, it is plus, and when you lose heat, it is minus. It
Yes.
is as with the money. Yes, when you get money, you are happy. It is a plus, a big plus. And when you lose money, it is a big loss, minus. Yes,
Mm-hmm. Yes.
so this is the rule here. And the mechanical work is vice versa. Why? What is the reason for this rule? The reason is the function of an internal engine, with combustion engine. The combustion engine needs heat in, meaning you must put some fuel for combustion, and you get what? You get mechanical work.
Energy. Mm-hmm.
So mechanical energy, mechanical work, and this uh, is also measured in joule and considered positive. So uh, the laws of thermodynamics are four: number zero, number one, number two, and number three, but they are four. The first law is if A is equal to B and B is equal or in equilibrium with C, then A is equilibrium with C. Yes,
We see. Yes.
it's a general. The first law is attesting that one form of energy can be turned in another one. So it is it doesn't indicate you a sense, or if this transformation is possible by 100% or no. The second law of thermodynamics uh, indicates you that it is not possible to turn some energy into another form by 100%. And the examples is you put heat into an engine and you expect to get mechanical work in the same amount. And this is not possible because always a thermodynamic source system must function in between two sources, in between two temperature levels, the heat source and the cold source. So the engine, in order to be a real engine and not a perpetuum mobile, must receive from the heat source energy. It turns as much as possible into mechanical work, but a specific amount goes to the environment or to the source, to the cold source, and it is lost. So this idea is very important and is expressed in the frame of the second law of thermodynamics. The term of entropy is developed, entropy, I don't know how you will symbolize it. We are symbolizing it with S, but there are countries where the symbol is H. So it will be a little bit tricky for you, but you must go deeper and understand the word, not the symbol. So entropy is heat divided by temperature, because one principle of thermodynamics says that heat goes from only by itself with no external intervention from a hot to a colder body, and vice versa. It is not possible by alone. It is possible, but you must put some energy into this heat transfer. So as a natural phenomena, the heat goes only from an upper level to a lower level, like water. Water doesn't climb the mountain, water comes down the mountain. Yes? So I'm very happy you understand, and I see your face that you are nicking, meaning that you are understanding. Yes?
Yes, of course.
So when you don't understand, please uh, let me know. Yes?
Okay, perfect.
Uh, so, and the fourth principle of thermodynamics uh, indicates that only at 0 Kelvin the or 0 Kelvin, that is a level of temperature that never can be reached, at least in practice. The, all activities of internal activities of the uh, substance are dead, nothing is moving, and then the entropy can be counted as zero. So we have four principles of thermodynamics, and separately we have also a law for the entropy. A question is also about gas mixture. Gas mixture means what? You take two gases that normally do not uh, react each to another, and you mix them. The first you uh, presume that they have the same temperature and the same pressure, not to have any problem with this phenomena. In this case, you will see that uh, the mixture of two gases is an irreversible process. You cannot imagine that by themselves the gases from a mixture uh, uh,
Can be separated.
succeed in going vice versa back, each in its reservoir. It is not possible
Mm-hmm.
by alone, but it is possible with external intervention. So for the gas mixture, you have here in the curses some indication. For example, this, do you see the screen?
Yes.
Yes, and here I made a sketch. It is in English. The mass friction, the volume fraction, not friction, fraction. Yeah? And here are the formulas. In order to use these formulas, you need some values from the tables. from, for example, m, the molar mass, or air, the constant of the gases. So you will find them here. Here, it is the table on page 221. You can write it down. And here you find the gases, you see, but you will recognize the gases with the chemical formula better, yes? And here is the constant of the gases on this, yes? And here is the heat capacity at pressure, constant pressure, at constant volume. Yes, here is the mass, the molar mass. Yes, so you will need all these values during the calculations you will receive. So what can you do? You can, for example, I will show you how you can do. You make a screenshot, yes? A screenshot. And then you go to paint. You see my screen?
Yes.
Make paste. And you got here what you need, yes? So then you take and first of all, you cut the rest, what you don't need, yes? Okay, you make copy, then new, file new, don't save, paste, paste. So now you have only the table. You see?
Yes.
First of all, you make file, save and I will save it as example in your here is that. So example of how to use thermodynamic tables, yes?
Okay.
So you solved it, yeah? Here it is. Then you make, okay, it is PNG. Let's make it GPD. Yeah. Save. Okay, now you close and go to your, where is it? Here. We are opening, yes, here it is, you see it?
Yes.
And then you say open with what you want. Let's say with Adobe Photoshop, okay? It takes a while. And here it is now. Now we are going, okay. And we try to rotate, edit, where is it? View, file, close, share. I don't know exactly now where it is, but you can rotate it.
Yes, of course I can.
You know, you can make it larger. Oh, now it is difficult to work. Oh. Oh, stroke lawyer. Okay, you have to turn it and to let's go back to no. Today I had I lost it. Okay, I think here in Paint you can use letters to write. So first you are using, you can cut, yes, and then you can write. You can write over the Romanian word, the word in English you need. This is only if you want to have this specific table in English, yes. But if you find somewhere else, you can use also other tables. But on, do you have possibility to type some pages? Can you type pages? Print? Can you print out?
The voice stopped.
The voice? My voice is okay.
Yes, now it's okay, but I just heard the print.
Okay, so my question was, do you have possibility to print?
I guess there is a near place in
A
here. I think.
printer, yes, because the last in situation is you go to print some pages and then write you with your hand down what do you think it is needed. For example, this table is needed. Yes, you can go with the file and let the gentleman said, okay, this table and this and this. So if you want, I can dictate you the numbers of the pages that you need. Should I dictate you?
Maybe yes. I already saved this one to one.
Okay, I will, I take my book and I can give you a short list now for the start. Yes, but as I told you, you can use them. So write down 204, 205, 206, 207, 8, 9, 10,
Mhm.
11, up to 11, 211, only the first table
Okay.
for the moment. Then 219,
Mhm.
220, 221, this is the most important,
Yeah.
222,
Mhm.
I don't know exactly if it's at this moment, or sometimes you will need also the tables on page 223, 24, 25, 26.
Mhm.
And after that, you need very important tables 227, 28, 29, and so on, up to 242 included.
Okay.
And you will need also the diagram on page 245,
Mhm.
and the next one, 246. This is, let's say, a minimum. And at the end, two hundred and 248, approximately everything. Yes. So based on these tables and values, what you receive as calculated examples from me, you will find the data here. Of course, these are international data, but sometimes from one version to another, small differences can exist.
Okay.
Okay, so basics on thermodynamics. In this lecture, I give you the information: what is energy, what is the what, which are the units, that we have potential, kinetic, and these are external energies, but we have also internal energy, and this is energies that you must have in your mind as a spare room.
Mhm.
It is, how to say, if you have uh, because let's say you are a thermodynamic system, and you have in the bank you have 500 lei. In your pocket you have only 100 lei, and you are going shopping, and you want to buy something that costs 200 lei.
The
What?
last thing I heard, in the bank I have 500.
I don't know what, because by me it's okay.
I don't know. Sometimes it's tough.
Okay, now do you hear me?
Yes.
So you have 100 lei, in the bank 500, and you go shopping, and you want to buy something that costs 200 lei. So there are two possibilities in order to buy these 200, what you want to buy, yes, to pay for it. You use your 100 lei from your own pocket, and you can borrow from somebody 100 lei. This is a possibility. But the best possibility is you take from your bank 100 lei. The final is you are shopping what you want, but your internal capacity, your bank account helped you. Your bank account goes down in value. This is the role of the internal energy. It is your bank for energy. So you have it. You can use it when you want. It increases or it decreases with temperature. The internal energy for perfect gases is depending only on temperature. So if the temperature is constant, for example, in the isothermal processes, the internal energy is constant and the variation of internal energy is zero. So what is the system and what is the environment is what is the boundary of a thermodynamic system. The system is a quantity of matter, of mass. The environment is everything that is outside the system. And the boundary is the separate imaginary surface between the system and the environment. And here you have two examples, a closed system and an open system. Open system is a turbine. The turbine is represented here, inlet, outlet, the volume of control, the controlled volume. In an open system, we have always a flow, meaning the same constant flow goes through the system, but every second it is there are another molecules. Only the flow is constant. Do you understand?
Not very much, but
So in an open system, it is like in a pipe. You have a flow. So if you look to a molecule, yes, in this particular second, the molecule is in one place, and then the second, in the next second, it is somewhere else. And what we are analyzing is always the same place. So in her place, another similar molecule is coming, but it is not the same. In a closed system here, at limit, you can say always the same amount remains. You can make a contraction or a detention by moving the piston, and then this quantity of gas remains the same, but gets a larger volume or a less larger volume, a higher pressure or not, yes? But it is the same amount. This is the difference between closed and open systems. So a thermodynamic property is a characteristic of the system that you can measure. Of course, these properties must have the same values when the system comes into the same status. So they are unique. You cannot say that a thermodynamic uh, system has at T temperature T and pressure P density, and at the same pressure and temperature another density,
Mhm.
if it is the same gas. So the properties are fully representative for the system. Uh, so if you want to use uh, these properties in order to describe, to fully describe and represent the thermodynamic system, you must choose two independent intensive properties. Uh, Independent means they mustn't have any connection between them. Two, not one, not three. Two is the minimum. Yes, two. And intensive, these are values that uh, uh, properties that are not depending on the mass. I defined also uh, uh, what a fluid is. Fluid is liquid or gas. The state is a situation, condition of a thermodynamic system. Uh, so we learned about closed and open system. The state is defined by temperature, by pressure, by volume, by energy, enthalpy, entropy, and so on. I don't know, enthalpy, you will have the letter H or E. I don't know what you will use in your country.
No, I
Uh,
use H.
H. So, okay, because we are using English I in Romanian. So you will find noted in the textbook, in the tables, you will find I, English I. Yes,
Mhm.
not H.
For the H.
Write it down.
Okay.
Write it down. So properties, intensive, extensive properties. The intensive, they don't depend on the mass, and extensive, they depend on the mass. So the temperature and the pressure, they don't depend on the mass. If you, let's say, take the air in your room and divide your room into two separate chambers virtually, in each you will have the same pressure, the same temperature, but the volume and the mass are different in each subsystems. It is, let's say, half or at least a part of the uh, entire original uh,
Room.
room. Yes? So this is the difference between intensive and extensive properties. Specific values are values that are calculated per unit of mass. The intensive properties um, are the most known: pressure and temperature, high and velocity, but the extensive properties are, uh, for example, energy, heat, internal, volume, yes? And all these letters are capital letters. And when you turn the extensive properties by dividing with the mass, you get the specific values, and the letters are small,
Small.
not capital letters. So this is the difference. Here we have joule, and here you have joule per kilogram
Mhm.
as unit. This is the difference. So what is a process, what is a non-flow or steady flow process. It is a clear process, is a change in the state of the systems. Non-flow process is a situation that is real, but we are not using it in thermodynamics. We are basing all our study on steady flow processes, meaning a uniform mass flow rate flows from one state to another. So the cycle is an amount of processes, one after each other, but the uh, initial and final state are the same. So you are leaving from one uh, combination pressure temperature, go your way and come back to the same pressure and temperature. Is it like you are taking a taxi and you go, I don't know where, shopping, and come back to the same point? Yes, this means a cycle. Uh, a power plant is a cycle. A gas turbine is a cycle. It runs a cycle. The power plant uh, runs a cycle for real gases, for vapors. It is a very nice chapter. I don't know if we will get to learn it because this could be a big help for you. Uh, so here are examples. This is a steam plant, yes? This is a generator that receives fuel, heat in. The vapor generator is heating the water, is boiling the water, is turning the water uh, into steam, uh, and then the steam is superheated up to temperature that is characterizing the whole steam plant. The water is, the water input has a pressure, and depending on this pressure, you can find from tables I indicated you which is the boiling temperature, meaning the temperature at which the water turns into steam. And if you continue the heating, then you turn these vapors from uh, saturated vapors corresponding to the water pressure into, or to the pressure from the steam generator into superheated steam. And this superheated steam goes into the turbine. And in the turbine, you are turning the energy, the enthalpy of the steam into mechanical work, mechanical energy. In the steam generator, you turned the chemical energy of the fuel into the enthalpy and internal energy of the vapors. So here we have the first, let's say, transfer of energy, yes, from one form into another. Here we have another one. Finally, on this level, we manage to turn the heat in, the energy of the fuels into mechanical energy. And based on this mechanical energy, a generator can transform the mechanical energy into electricity. And we are happy because everybody needs electricity. From the turbine, the exhaust is what? Vapor, but with less energy and mixed with water. And you have to condense this mixture in order to recover the water and send it back to the pump and start the cycle again. This is named a condenser. It is a heat exchanger. The heat exchanger is transferring energy from this steam and water mixture to energy taken out by a second fluid that goes into the condenser cold and goes out heated. And this means that you gained, you produce also some heat from this cycle. And if you use this heat out here, you can say that this cycle is a cogeneration cycle. You heard, for example, this word cogeneration, yes?
Not sure.
Not sure. It is a system when from one source you cogenerate two things, electricity and heat. And this is a modality, you must remember, to turn theoretically a steam plant into the most efficient one, having an efficiency of 100%. This is only theory. In reality, if the system works in cogeneration, you can reach efficiency about 80. And if you don't use this heat, but this heat goes out, goes into the environment, it is lost, then the efficiency is only half, 40. So this is a big difference, yes? So I gave you this example as a basic example of a cycle, yes? And here you get the here you get another example, the gas turbine circuit, the closed circuit of a gas turbine. Here is the combustion chamber of the gas turbine. We say heater. You put fuel and air, and here a combustion takes place. During the combustion, the energy of the fuel goes exothermally into the heat of the flue gases. And the flue gases are hot, very hot, over 1000 degrees Celsius. And you send these hot gases to a gas turbine, not a steam turbine, a gas turbine. And the energy of the flue gases is turned into mechanical energy. So the turbine starts to rotate and carries what? Electric generator who is producing electric energy, and on the same shaft you are putting also the compressor, because when you organize here the combustion, you must put the air, the combustion air, preferably at a higher pressure in order to have the best possible combustion. So you need in this cycle also a compressor. And the gases from the turbine, from the gas turbine, are exhausting here, and they go to a cooler or to a it is a heat exchanger where from where the gases are cooled down in order to start a new cycle. This is a theoretical cycle. And here in this cooler, the heat goes out. Yes?
Okay.
So what are you seeing? That each system must have a source at higher temperature heat in, and another source named the cold source where heat goes out. You cannot make, unfortunately, a system only to put heat in and not to take heat out. Because this would mean that all the heat in goes in work out. It would be a total ideal case. It will be a perpetuum mobile. So the name of equilibrium, we have thermal equilibrium requiring uniform temperature, chemical equilibrium, no reaction, mechanical equilibrium, uniform pressure. So the thermodynamic system is normally in equilibrium with its surroundings, but at least inside of it, we have equilibrium, because otherwise you cannot imagine any interaction. So here are examples of what interactions are meant. In this examples refers to heat and work transfer. We have here a control surface, and here inside we have a mass of gas. This mass of gas is heated by rotating this system. Yes, you are rotating it, and in time, the temperature of the gases inside is goes up. Yes, so you conclude that you can turn mechanical energy into heat. Now, let's go vice versa. Let's go back. You imagine that you leave this gas with high temperature, and here is the propeller. And you expect that now that the gas cools down and puts the propeller into movement. Is it possible or not?
No, it's not.
No, it's not possible. That means that heat cannot turn into mechanical energy on our wishes. It is a thermodynamic law that expresses the conditions of this transformation. Yes? A process is reversible in thermodynamic or irreversible. But normally, most of the real processes are irreversible, but we are considering them reversible. Which are the causes of the reversibility or irreversibility? The existence of the friction. You can not get rid of the friction. The presence of the heat transfer, because always if you have a higher and a lower level of temperature, automatically the heat transfer occurs. As we cannot imagine that we have 0 degree Kelvin in two systems, only in that situation the heat transfer could uh, occur, but this is impossible. Combustion is also an irreversible process. Once a fuel entered a chemical reaction with oxygen or what else, you cannot regain the fuel. You have the gases and that's all. And also the expansion uh, of a flow. Let's think of a pipe. You have a pipe and suddenly the pipe uh, gets larger, bigger diameter. What is the gas doing? The gas is expanding and is very happy. It has more place. Yes. Then you uh, once this expansion happened for the gas, uh, it is impossible to go back to the initial situation by alone. Okay, you can put some energy in and bring it to the initial situation, but alone it doesn't go. So process is also irreversible. Uh, so we have mechanical, thermal, and chemical irreversibility. The most important processes in thermodynamics are listed here. Adiabatic, no heat transfer between the system and the surrounding. Isothermal, the temperature in the system is constant. You must think about P, pressure, volume, temperature, mass, and quality of gas. The quality of gas you cannot change. It is given, yes? The volume is not something very controllable because the gas is expanding. It takes the volume of the room, of the vessel where it is.
Yes.
Okay, so what remains is temperature and pressure.
Pressure.
Yes, so when the temperature is constant, you name the process isothermal. When the pressure is constant, isobaric. When the volume remains constant, the process is isochoric. When you have no heat exchange, it is adiabatic. During the adiabatic, all three parameters, pressure, temperature, pressure, and volume are changing, but no heat exchange. Q is 0. And the last one is the isentropic process. It is adiabatic reversible process named isentropic. That isentropic, entropy is constant. So it is an adiabatic reversible process. And all the others are polytropic. Here is the standard convention for heat and heat Q and mechanical work. So when you gain, it plus, and plus is when the system does mechanical work. It is a convention of the heat engine. So the transfer of heat is driven also by a temperature difference, and of course of also of entropy transfer that can be measured. So we have a boundary, a diabatic boundary that is such a boundary that uh, um prevents the transfer of heat, and another boundary is a diathermal boundary. The heat transfer is allowed, but no temperature variation in the system occurs. About the enthalpy, um, it is a quite, let's say, complicated notion, expression, value. It is defined as the sum of the internal energy and the product of pressure and specific volume. So it is the sum from U, internal energy, and the product PV. Here is an example when you have a reservoir and an empty bottle and may communicate the reservoir and the bottle, you will see that no movement occurs, the system remains in the same place, no nothing in temperature occurs. So Q and the heat and the mechanical work are both zero. But um, this example has its significance that namely that the internal energy of the gas in the reservoir made this process possible. So this is the internal energy U that is driving this process, and also the pressure and the specific volume of the gas are of importance. And this is the enthalpy of this system. Here are the formulas, yes? When we use small letters or capital letters, you must be attentive. Normally small letters for 1 kilogram. The phase, you can, for example, imagine ice, water in steam, and steam, the three possible situation in which H3O can exist. The three phases of water. The liquid droplets disperse into a liquid vapor mixture. Here is liquid, here is are the vapors. So when from the spark energy for the combustion is sent out, the reactants try to react, and no movement occurs, no heat transfer, but you have as a result the products. These phases are, this example gives you the impression of how a real gas can change the phase from gas to liquid and backwards. Examples of how energy can be turned from one form into another. From E1 to E2. Before steering, we have here a state. And after that, we are rotating. We have another state. But we didn't heat it. The exchange heat is zero. What we did, we put some energy into the system, some mechanical energy with this steering.
Okay.
And from this mechanical energy, we concluded that the systems turned into another situation, E2. So here we have one temperature, here another. This is higher. Yes? So even the heat exchange is zero. We got an input of mechanical work that is negative, and the conclusion is that the temperature in the systems goes higher, meaning the internal energy raised. Here are some other examples, but here for the moment we will skip them. Again, the example of the gas turbine and how you can recover energy from the gas system in order to get a better efficiency. Here you have another example of how energy is transformed. This is what? What do you see here? A cylinder. And this is the system from an internal engine, the crankshaft, yes? Do you know how it works? This is a piston.
Yes, as it to rotation.
Yes. So here is air and fuel. The combustion takes place. The gases resulted are pushing from left to right the piston, and the translation movement is turned into rotational movement. This is the principle of the engine, internal combustion engine. So from chemical energy, you get mechanical energy of rotation. And here are the flows of energy. In, out, the gases are going out. You can cool this system, and then you can take from the or use from the cooling water the temperature. So you get from the same inlet both mechanical energy and heat. If you use this heat from the cooling waters, now it is a system. In your country, the energy system is based on what? On solar energy or on what?
I guess yes. So gas
And gas also?
yes.
Yes, so, but not coal.
No, I don't think so.
No, no, no. Okay, because you must look what would be interesting for you to learn. Or I think solar energy, yes, could
Yes,
be used because the climate is much hotter than here. Yes, it is hotter. Yes.
of course.
Uh, so this was also an example. Here is a nuclear power plant. Very interesting. The nuclear power plant, we are analyzing it in order to see the streams of the energy flows. This is the objective. A nuclear power plant has always two separate cycles. You see them. Here is one and here is another. But they are interconnected by a heat exchanger, meaning heat can be transferred from one part to another and vice versa. So here in the left part, we have a system that is running with steam. We don't have any boiler. We have only a heat exchanger that brings heat and turns the feeded water into steam. The steam goes into the steam turbine. The steam turbine is rotating the electric generator, and we have electricity here. The rest of the steam goes into a cooler, and the cooler allows us to take some heat energy out of the system. And this part, we say it works in cogeneration. It produces electric energy and heat energy. If it produces only electric energy and no heat energy, if you don't use this heat energy, because this heat energy is always produced, yes, but in order to use it, you must have a need for it. In your country, you don't need to heat as much as here. In Romania, we are working in cogeneration almost during winter, when we need this heat to warm up the houses. Yes, or you can use this heat in industry. Then you can use it also during summer, because industry works all over. Yes, and then the water that condensed in the condenser goes to the pump and is fed into the cycle back. Yes, let's analyze what happens here. So here we have water and steam, and in the nozzle we have a gas. It is here an example CO2. It has nothing with CO2 from the atmosphere. It is a gas that is filled in this system. The CO2, as other gases, has the possibility of changing its phase. It can turn into liquid, from gas into liquid, and from liquid into gas. And when this happens, the energy is exhausted or energy is needed. So we have here CO2 gas, and from the reactor, nuclear energy is warming up the gas. The gas uh, uh, goes then into this um, heat exchanger, and the energy, the heat is extracted, and it turns into liquid. So here we have gaseous CO2, here we have liquid
Liquid.
CO2. And by this, when this happens, a lot of energy is exhausted from this part and goes into the steam part. So that's why you don't need here any more other energy source. So this is a nuclear power plant. Here is a reactor, and here we have the input of energy, uh, nuclear energy, that is the source of the heat to turn the gas into uh, liquid, and the liquids finally back into the gas. And this exchange of phase makes possible this, that heat is exhausted that is used in this second cycle. So this is a gas-cooled nuclear power plant uh, because the CO2 is meant to cool down this core, the core of the reactor. So this was a slide, the last slide. Okay, okay. So um, so we made basics, the first law. Um, let's take uh, this one. I already indicated you some ideas. What time is it?
Oh no.
Don't know.
It's 10 minutes to 8.
Okay, so this is the last PowerPoint, yes? So ideal and perfect gas, I told you about that. Uh, Idealized gas, it doesn't exist. Um, it is meant such gas that the molecules uh, uh, are elastic spheres in conservative mechanical systems. They don't have any collision each to other, but in reality, this is not happening. So the perfect gas is a real gas that has some of the properties from this model. So the fundamental values, properties that we will use: pressure, temperature, volume, internal energy, entropy. For all these, you must make your own picture and you know all the units.
Mhm.
This is the equation of state, or the thermal equation of state. PV small v or PV capital V, then M is here. P pressure in Pascal, V volume in cubic meter, M kilogram, air from the table. From the table, I told you the page. You wrote it down. It is the most important one, page 221, 221. And teach the temperature in Kelvin. The rate between the capacity at constant pressure and constant value is named how?
Lambda.
Adiabatic coefficient. Yes, lambda. But I don't know. You will find this in the table named with K. Have a look at this 2 to 1. In the last row, you will see exponential adiabatic. This means adiabatic exponent. Here in the tables, it is marked with K, but it also this letter, Greek letter, can be used. Yes, the difference between each is the gas constant. The gas constant is not the universal gas constant. The gas constant is specific to each gas, and the universal gas constant is for all gases the same. The units are different. Air, the specific gas constant, joule per kilogram and Kelvin, and the general, the universal gas constant is joule per kilomole and Kelvin. Totally different. Here are examples of air and the capacity at constant volume for different gases. Yes, this is also an example. As you see, in each thermodynamic book, you will find some useful tables. About the van der Waals equation for real gas. In reality, all gases are not perfect. And then van der Waals tried to replace oh to find out a thermal equation of state as this one, but for real gases. And he found this one. So from V, we are subtracting the volume of the molecules, air and T remain, and to the pressure, we are adding an amount depending the so-named kinetic factor, kinetic viscosity. So these are the formulas that you don't need to know by heart, but you must all understand them. Here is the first and second law of thermodynamics. Here is the expression for perfect gases for the variation of internal energy and enthalpy. Cp, Cv, calculated based on the constant of gases. The formula for the heat exchanging, where we use the polytropic capacity, heat capacity, Cn, not Cp, not Cv, Cn. And here are the formulas including the entropy. TdS TdS is equal to heat. So, and for all learned isochoric, isothermal, isobaric, and adiabatic processes, the difference in between is the value of n. N can be 1, 0, k, or infinite. And in general, we speak about a polytrope process, polytropic process. What you must know are the formulas, but again, not by heart. You must understand them. Here are the formulas for the polytropic transformation. One formula, second, and third. And here are the formulas for the internal energy and enthalpy change that are, as you see, depending on the only on the temperature difference. And this is a relation of Robert Meyer. You see it, yes?
Yes.
Cp equal to Cv plus R. And here are all the other relations that you must learn not by heart. You must learn how to use them. Yes, you can find them where whatever you are looking. Also in the second or third table that I indicated you from this thermodynamic book. Yes, the tables. Yes, you will find all these formulas there. Important is how to use them. So as I told you, n can take different values, 0, 1, plus, minus infinite. And this tape, this is here very, very important. You must know to represent in PV and in TS all these 5 processes. So let's take one point here. A vertical means volume constant. This is a isochoric. And horizontal means pressure constant. It's isobaric process. When you have an isothermal process, this is an isothermal process, it is hyperbole, equilateral hyperbole, meaning equal distance from the axis. Yes, this curve that is more shaped, more vertical. This is the adiabatic process. And what is left, whatever, is a polytropic. The problem is if we are putting n here, plus infinite, 0, minus infinite, so we see here are plus values for n, here are negative values for n. Yes? So here are positive values for n, the same as here, and here are the negative. So if you make a curve like this, it is for sure a polytropic with n negative. If you make it like this, for example, yes, yes, you will see what?
Positive.
Yes, positive. And now the same in TS. S constant is adiabatic reversible process. N is equal to K. This is reversible adiabat. Horizontal means T constant isothermal. V constant is a logarithm curve like this. And P constant is a linear curve like this. Now be very attentive. In this PV diagram, here we represented the isotherm, yes? But if you are having a bigger isotherm, not let's say 300, let's take 400 degrees. It will have the same shape, but it will be in this direction. Yes, in this direction, T is going up. Do you understand me? The isothermal are families. So as you can make different verticals, and if you go this direction, the V is growing and growing, yes? So for the temperatures, if you want to see a higher temperature, it is a curve like this, but it goes in this direction. If you go backwards, the temperatures are smaller. Do you understand? Yes? And here, you have to know that if you have here isochoric process or transformation, and you want to represent another isochoric transformation with a higher value, it is like this. It goes in this direction. And for the pressures, it goes in this direction. This is very, very important. Yes. We will make some exercises in turning. Oh my God, it's my phone, excuse me. I forgot to cut off my telephone. Okay, yes. So for today, I hope you understood something at least. So take your time to go over oh, all the lectures. Here they are, yes. Some of them we made today together. Make this essay as much as possible. Look here, the problem solved, but you must not read them. Take your pen, take the computer and calculate by hand.
Mm-hmm.
calculate by yourself.
Okay.
Don't trust me. Yes. And I will give you also uh, a list of open sources that I liked from the internet, and then you can listen to what else you want.
Okay.
Yes, it's okay for today. So we are finishing the lesson, and I wish you all the best.
Thank you.
The next lesson will be when?
11,
Let's
I guess.
uh, on uh, on Monday. Yes,
Yes, exactly.
on Monday. Yes, and the next on Friday, because Tuesday, Wednesday, and Thursday you have the other classes. But you must be very ambitious, because we have to run through thermodynamics. Yes, this is the expression. Yes, because in 3 weeks you must go with at least some basic elements back. Yes,
Mm-hmm.
this
Okay,
is
okay.
a very important lecture for your future, because
Yes,
you
yes.
are studying uh, electroengineering, as I understood. Yes,
Exactly. Yeah.
so you want to work with energy and to gain some good money. Yes, and that's why you must learn. uh, don't think that I will not let you through, but please make possible that all your time is dedicated to thermodynamics. Yes?
Okay, okay.
Yes. So I will be happy if I can give you not only the credits, but also a good mark. Yes?
I hope I will deserve.
Okay. So do you have any questions
Thank you.
for today? No. So let's wish you a nice weekend, a nice fruitful weekend, because you have to uh, work hard until Monday. Yes,
Okay, I will.
it is Monday at what time?
Yeah, I think 5 and 30 minutes.
6:30.
6:30.
6:30. Yes. Today it was 5. 6:30. Yes. But today I had 3 lectures. I'm totally out. Okay. So bye bye until
Thank you.
next time.
Thank you. See you.
See you.
Bye.